Hey, welcome back. This is Charlie Thompson, and this is part 2 of the water and atmospheric moisture slide video narration extravaganza. I hope you like it. So, air masses. Let's talk about air masses. Hi, welcome back. This is Charlie Thompson, and this is part 2 of Atmospheric Water and Weather, Chapter 4. In the second part, we're going to talk about air masses, which are huge blobs of air that have uniform temperature and humidity characteristics. We'll talk about processes that lift air up to make it rain. We'll talk about mid-latitude cyclones, which are the storms that we get in the winter. Talk about weather forecasting briefly, and then we'll talk about violent weather. So first off, air masses. Air masses, the name tells you everything you need to know about the air mass. They have a 2-letter system for designating air masses. The first letter is lowercase, tells you how humid that air mass is. M for maritime, from the ocean, maritime, moist. C for continental, it's inland and it's dry. So the first letter tells you the humidity. The second letter is uppercase. The second letter tells you temperature. You have a T for tropical, where it's hot, a P for polar, where it's cold, or an A for Arctic, where it's super cold, or AA for Antarctic, but we're clearly never going to get that air mass in Sacramento. So, I keep saying they're continent-sized blobs of air. They extend half the thickness of the troposphere. They're about 6 to 9 kilometers thick. Within the air mass, the temperature and humidity is uniform. So if you took air samples throughout the air mass, the temperature would be about the same throughout it, and the humidity would be about the same throughout it. When two air masses meet, if they're different in terms of temperature and humidity, they don't mix. They form a boundary layer called a front. The polar front is caused by the warm air coming out of the tropics, colliding and not mixing with the cold air from the poles, making the polar front. So let's look at some sample air masses. For California, the two most important air masses are this maritime polar, temperature about 10 Celsius, specific humidity 4 grams of water vapor. Colliding, or rather the maritime tropical, is usually the collider coming up out of the tropics, colliding with this cold air. It's 28, 25 degrees, so it's warm, specific humidity 13 grams. Over here, with warmer ocean temperatures, there's more evaporation, more water vapor, so the specific humidity is higher. And this is the summer pattern. In winter, and also I should point out the continental tropical, 13 grams of water vapor. As it moves inland, the air is going to get lifted up, you're going to get rain, the air is going to get drier, so now the continental tropical air has an average specific humidity of 10 grams. Once it moves over the ocean, it's going to pick up water vapor off the ocean, and it's going to get up to 17 grams. In the winter, everything shifts south, or rather in December, everything is going to shift south with the subsolar point. So now we've got maritime tropical, maritime polar, maritime tropical. Continental polar, that's really cold and dry. Specific humidity 1.4 grams, but it's nothing compared to this continental Arctic, which you're only going to get in the northern hemisphere and only in the middle of a continent. It's extremely cold, extremely dry. Average specific humidity 0.1 grams of water vapor per kilogram of air, as opposed to 14, or I think it was 17 in the summer for maritime. So as you go farther north, there's just less energy to evaporate water vapor, so it's just drier and drier and drier. So as those air masses move along, they reflect the temperature and humidity of the place they came from. Like if they come off the ocean, they're going to be moist. If they come off a tropical ocean, they're going to be warm and moist. As they move inland, they're going to dry out. So they slowly take on the temperature and humidity of their new location. If they move inland, they're going to get drier. If they move towards the poles, they're going to get colder. If they move towards the tropics, they're going to get warmer. And that's called the process of air mass modification. And one of the examples of air mass modification is lake effect snow, which makes these amazing visual images. These are the Great Lakes in the Midwest. Here is Chicago right in there. So what happens is you've got this extremely cold, dry air blowing over the surface. As it moves over the Great Lakes are made of water, and so there's evaporation. So they pick up the water vapor, and then the water vapor condenses because of the colder air, and you get lots and lots and lots of snow downwind of the Great Lakes, and that's called lake effect snow. So these are called cloud streets. These big streaks of clouds coming off the Great Lakes are cloud streets. In this diagram, we're looking at the average annual snowfall. So like Duluth, they're getting 60 to 99 inches of snow, but downwind at Sault Ste. Marie, they're getting 100 to 130. My favorite example is Detroit versus Buffalo. Detroit, they're getting 2 to 3 feet of snow. Buffalo, they're getting over 10 feet of snow every year. So I look at that and go, oh, right, Detroit. If you're going to put an auto manufacturing center someplace, would you rather put it in Detroit with 2 to 3 feet of snow or Buffalo with 10 feet of snow? I'm going to Detroit. Oh, and then right here, those are the Appalachian Mountains. Slightly higher, so the air gets lifted up a little bit more, so you get a little bit more condensation, a little bit more snowfall as the result of what's called orographic lifting, which we'll talk about later. Long story made short, the air runs into the mountain, it gets lifted up, you get rain. So yeah, that's often, so these right there, that's lake effect, that's lake effect, that's lake effect, because they're on the downwind side. Right here, there's no lake, right? But there's higher snowfall, and the high snowfall is because of the higher elevation from the Appalachian Mountains. I also want to talk about climate change and lake effect snow, and how climate change is increasing lake effect snow. So global warming is increasing lake effect snow, and it works a little something like this. In the past, the Great Lakes were cooler. Because they were cooler, they got cold in the winter faster, so they would freeze over. Once they freeze over, there's a layer of ice, so there's no more evaporation, so the lake effect snow shuts down when the Great Lakes freeze over. Because of global warming, the Great Lakes are warmer. Because they're warmer, they're freezing over either later in the year or maybe not at all. And because they're freezing over later or not at all, this open water persists, so the lake effect snow is increased because there's open water because of global warming. So there's more snow caused by global warming. That's amusing. Processes that lift air. If you want to make it rain, you need to lift air up. And the reason for that is if you want to make it rain, you need to have condensation. In order to get condensation, you need to cool air to dew point temperature. And if you want to cool air, the only way to do it pretty much is lift it up. So if you want to make it rain, you need to lift air up. Processes that cause air to cool to dew point. Yeah, there's 4 lifting mechanisms: convergent, convectional, orographic, and frontal. So those are words. Words are great. Let's look at some pictures. So convergent is when the air comes together, converges, coming together, and rises. This would be, for example, along the intertropical convergence zone. So you can imagine this is like, these could be the southeast trades, these could be the northeast trades, and then the air is rising in the ITCZ. Or it's just any area of low pressure. With low pressure, the air converges and rises. So number 1, convergent. For example, right here with the ITCZ, air is rising, it's converging, and it's rising. Convectional. So convection, you remember, as a mechanism of heat transfer. Convection, the air gets warm and it rises. That's pretty much it. Local heating, it could be a small scale effect, like just on this field, because it's darker and because it's plowed and it's all churned up, there's more moisture. That's going to evaporate and then condense and release heat, causing the release of latent heat, which is going to warm the air, so it's going to rise more. Or it could be land-water heating differences. I was going to say, I really hope the next picture is convection over Florida. So you can see over the ocean, not a lot of clouds, not a lot of little cumulus clouds. These are cumulonimbus, the larger ones, and these are smaller, just cumulus clouds. So these are all cumulus. And some sort of tropical storm spinning off of the Florida coast. But it's the difference in the number of clouds over the ocean, which is hard to heat up, versus over the land, where it's easier to heat up the land. So because you've got this long peninsula that's heating up because of the sun, you've got hot land, cooler water. So as the air rises, it pulls in this warm, moist air off the ocean that then rises, which pulls in more, which rises. So Florida, if you like thunderstorms, Florida is a great place to go. Another view, another day. This is also taken from space, showing the difference. In fact, you can see Lake Okeechobee, massive lake in the middle of southern Florida, that's not heating up. So there's no convectional activity over the lake. There isn't over the ocean, but there is over the land. That's just a great picture. Okay, orographic lifting. Orographic means it's getting lifted by a mountain. This is the most consistent. If you want to make it rain regularly, the best thing to do is to put a mountain someplace where it's going to get wind on a daily basis. The air runs into the mountain, it gets lifted up, it cools. Doesn't matter if it's stable, unstable, the mountain doesn't care. It's just sitting there and the air is blowing up over it. So as long as the air is being lifted by a physical barrier, it keeps cooling, you keep getting rain, it keeps cooling, you keep getting rain. As soon as you run out of lifting, you run out of rain. And even worse, or better, I guess, I don't know, is as the air rises, it cools, but then as it sinks, it heats up. So as it heats up, the relative humidity goes down, the clouds evaporate, the rain stops, and you get clear skies. On the rain shadow, this is the rain shadow side of an orographic barrier. So this would be Nevada, this would be eastern Washington, this would be eastern Oregon, this would be coastal Washington. The dry side is the rain shadow side, and these downslope winds, Chinook winds, they're called in the Pacific Northwest. In Europe, they're called Föhn, F-O-E-H-N, Föhn. And these are those downslope winds. We get them as Diablo winds, although they should be going the other way, down into the Central Valley. So when the winds come out of Oregon and then spill over the Sierras and drop into the Central Valley, they get compressed and they heat up. This is also what kicked off the fires in Oregon in August and September of 2020. These downslope Chinook winds, as they drop, they're going to heat up 10 degrees every kilometer. So if they drop 3 kilometers, they're going to heat up by 30 Celsius degrees, which is like, what, 58 or so? So enormous amounts of heating as the air sinks. In fact, the most rapid temperature rise ever recorded was 49 Fahrenheit degrees in 2 minutes. 49-degree increase in 2 minutes recorded at Spearfish, South Dakota by one of these downslope winds coming off the Rockies. So as the air came off the Rockies, it sank, heated up, sank, heated up, sank, and heated up, and increased the temperature 49 degrees in 2 minutes, 49 Fahrenheit. Orographic lifting, as the air goes up, it expands and cools. If it sinks, it's going to get compressed and dry out. And those downslope winds, Chinook winds. So an example, here we've got a Google Earth shot showing the ocean, the windward side of the Cascades, and then the leeward rain shadow side, like Yakima. They get 8 inches of rain. Over here, Mount Rainier, they get 126 inches of rain. So literally, a temperate rainforest as opposed to steppe and kind of semi-desert scrub. Oh, one of the rainiest places in the world. This is Mount Waialeale on the island of Kauai. They get 486 inches of rain because every day the trade winds come and get lifted up by this, and they get 486 inches of rain. The rain shadow side of Kauai gets about 20 inches a year. 486 inches a year, 20 inches a year. So this is right in here, the actual weather station on the top of Mount Waialeale. The helicopter pilot said, oh yeah, you can see the sun's been out for a couple minutes because the vegetation's turning brown. We were hovering and the winds were blowing sideways at 50 knots. And the helicopter pilot said, yeah, there's only a couple days, only a couple flights every year where you can see the summit when it isn't socked in with clouds. This is what 486 inches of rain a year looks like. I was guessing jungle, huge trees and vines, but no, it's like moss. It's just way too much. The wet side of Mount Waialeale, if you like ferns, it's a great place to go. And then the dry side, the rain shadow. This is the native vegetation. In California, very similar. The two patterns in California are latitude under the polar front, latitude under the subtropical high, and then elevation. So you can see like the transverse range with more rain down in Los Angeles, the transverse range. We've got the coast range. You can see the coast range with more rain. You can see the Sierras very clearly. And then you can see the Trinities and the Klamath Alps, and then going up into the Cascades. So Nevada, here's something fun to think about. 30 million years ago, the Sierras were not the mountain range that they are now. It would have been flatter, like much, much flatter. So that rain wouldn't have gotten stopped by the Sierras, and so Nevada would have been way wetter. Like, where'd it go? There's Death Valley. So here's, you can't really see Death Valley from the precip, but it's on the dry side. Like, to get to Death Valley, you have to go up and over the Coast Range, which filters out a lot of the rain, and then up and over the Sierras, including the highest point in California, Mount Whitney, the highest point in the lower 48 states, just over 14,000 feet. And remember, once you go over a mountain, in order to get more rain out of that air, you have to cool it more, and the way to cool it more is to lift it higher. So once you're over the tallest mountain in the lower 48 states, you're not getting any more rain out of that by lifting it by a mountain. So the rain shadow, the Central Valley, the rain shadow, Nevada, the rain shadow, Eastern Oregon, Eastern Washington, Northeast California. Frontal lifting. It's when two air masses collide, they make a front. You've got warm fronts, and fronts are named for the more active blob of air. So the blob of air that's moving along, that's what the front is named for. So if you have a warm blob of air moving along and colliding with a colder blob of air, it's a warm front. If you have a cold blob of air moving along that collides with a warm blob of air, that's a cold front. So we got warm fronts, where a warm air mass moves into a cold air mass. The warm air moves up and over the cold air. Warm fronts are about 1,000 kilometers wide. They move about 25 kilometers an hour. Here is the diagram out of the book of a warm front. They move along at 25 kilometers an hour. Here is the warm air that is slowly trying to push this cold, dense air out the way. And there is this distinctive set of clouds. First, there are cirrus clouds. So you have to imagine this entire system is moving from left to right across the screen. The cold air is going to get gradually pushed out of the way. So if you were standing here at the right edge of the screen, you'd see cirrus clouds, and then as the storm goes by, you'd see cirrostratus, altostratus. As they get lower and lower and lower, finally stratus, and then rain. And if you think about the way our storms come, usually 24 hours out, you see cirrus clouds with those wispy effect. Halo or a ring around the sun or the moon tells you 24 hours later you're going to get a storm. That's because cirrus clouds are at the leading edge of a warm front. So you have cirrus clouds, and then as it moves along, you can see that the altitude of the clouds just gets lower and lower and lower, and then you have gradual gentle rain. So from the actual boundary layer on the ground to the cirrus clouds, about 1,000 kilometers. With a cold front, the cold air mass moves under the warm air mass. The cold air lifts up the warm air. In fact, the cold air is always lifting up the warm air. Warm air is less dense, so whenever warm air and cold air collide, the warm air is going to get lifted up. Cold fronts are about 400 kilometers wide. They're more narrow. They move faster. They travel about 40 kilometers an hour. So here we've got a cold blob of air moving along and lifting up this warm air. So it moves faster. The air gets lifted faster. So you get heavy rain for a little bit, and then you have clear, cold air behind. And if you think about the way our storms end in California, typically it like pours for a while, and then you wake up the next morning and it's clear blue skies and it's cold. And it's cold because it's this cold polar air mass. From the cold front, they're about 400 miles wide if you look at it on a weather map. And here's the symbol for a cold front, those blue triangles. Probably should have said. Symbol for a warm front, you can't see it. We'll have to look for the video. So I'm going to start with this warm front. So if you were standing here, the warm air is going to push the cold air out of the way. And so if you notice, the altitude of the clouds is just going to get lower and lower and lower and lower until you end up with the nimbostratus rain clouds. If I back it up for the cold front, it's moving faster. The warm air gets lifted much more rapidly. So you get intense rain, often thunder, lightning. I don't think we get that too much in Sacramento, but that would be associated with a cold front. And then it's just cold, dry air behind it. I've put the animation in the lecture slides. So when you watch the lecture slides, I would watch the animation and it's got narration. I would turn it on and listen to what Pearson has to say about cold fronts and warm fronts. So here's a cold front moving along. That's a cumulonimbus cloud. There's another one. Looks like they've got a bunch of cumulonimbus clouds embedded in the front end. It would be moving from the top down. So there'd be warm air in here that's getting lifted up as this cold air is moving towards the bottom of the page. More lifting of air. This really impressive Midwestern supercell. Probably tornadoes are going to be spawned from that. Big hail. So if you put a cold front and a warm front together, you get a mid-latitude cyclone. Mid-latitude tells you what latitudinal zone it's in, the mid-latitudes. And cyclone tells you it's air flowing into an area of low pressure. So it's a warm front and a cold front spinning around a center of low pressure. And they're caused by the conflict between the warm maritime tropical air mass and the cold continental polar air mass. So it's the conflict between the natures of these two different air masses. And once that conflict is resolved, the whole storm goes away. So here we've got a warm front. So you've got warm, moist air coming up. You've got cold, dry air coming down. There's a center of low pressure here. This is the symbol for a warm front. This is the symbol for a cold front. And this is the symbol for an occluded front that I haven't talked about yet. So we've got warm air getting lifted up over the cold air. And then over here, there's cold air pushing along, moving along the ground. That cold air is running into this warm air and lifting up the warm air. This was a satellite picture from this year with a cold front and a warm front and an occluded front over in here someplace. So the whole system would be rotating counterclockwise. And this warm air is coming up. And here's the boundary layer between the warm air down here and the cold air up here. So the warm air is running into the cold air and getting lifted up, making a warm front. So you've got all this warm air down here. Over here, you've got cold air coming out of the poles, and that cold air is moving along. And as it moves along, it's going to run into the warm air and lift up the warm air, making a cold front. You can see behind the cold front, it's clear. So this would be the day after the storm, when it's all clear and you've got blue skies and cold air, because that cold air is coming out of the poles. I have put a whole bunch of examples for you to take a look at. If you click on it, it'll open up earth.nullschool.net. And it'll take you to an example of exactly what we're talking about. So I'll click through a couple. So right here, you've got warm air coming up, colliding with cold air. And then over here, you've got cold air coming along, colliding with this warm air. And if we turn on temperatures, 16 degrees, 11 degrees, not a huge difference in temperature differences. If we turn on the total precipitable water, you can see that there's pulling. The warm air is bringing moisture up, and the cold air is not. The cold air is very dry, and the warm air, 33 kilograms of water, 10 kilograms of water. Let's look at another one and see what happens. Oh, there's two. Oh, yeah, so fronts are pretty easy to find on weather maps, especially the animated ones, because the wind direction changes 90 degrees. So here's this warm air coming up, warm air coming up. There's the center of low pressure. And then this is that cold air coming down that's running into the warm air. So there should be a line of clouds here and a bunch of clouds over there. Same deal here. Got cold air coming down, warm air coming up, an area of high pressure, rotating clockwise, low pressure, rotating counterclockwise, high pressure, rotating clockwise, low pressure rotating counterclockwise, high pressure rotating clockwise. And then down here, this is actually the ITCZ. You can see the northeast trades moving down, and then these would be the southeast trades moving up. So if I turn on the total cloud water, aha, you've got a cold front, relatively narrow cold front, and a big old wide warm front. And then, as I said, along the ITCZ, you've got all these convectional clouds. So I've put a bunch of examples. I hope you enjoy that. I hope it makes sense. If not, show up to Zoom. Give me a call. Whatever. Let's hang out. Let's look at wind and rain patterns. Here is another animation. I think this is so useful because I can't draw this on the board, and even if I could, we're not in class together anymore, so we don't have a board. So, cold front, warm front. Here's the warm air coming up. Here's cold air, cold air, cold air, warm air, warm air, warm air. The whole system is going to rotate counterclockwise as it moves across the United States. So there's two patterns of motion with these storms. In fact, if I go back and we scroll forward, you'd see that the whole system is going to move from west to east. It's going to move across the country. This is over 2 days. So typically it will take a week to move across the whole U.S. The cold front, you can see, is moving faster than the warm front. So it actually catches up to it, and then all the warm air is going to get lifted up, and you have an occluded front behind it. When the cold front passes the warm front, because the cold front, remember, can move at 40 kilometers an hour. Warm front's moving 25 kilometers an hour. And in just a second, they're going to turn on the side view that I think makes this entire video worthwhile. Yeah, let's get going. There it is. Okay, so as it moves across, as it moves along. So here we've got cold air. That's this cold air. That cold front is this cold front. This warm air is up here. This cold air is the cold air along the ground. So the warm air is moving up over the cold air. The warm air is moving up over the cold air. And then over here, you've got the cold air lifting up the warm air. So the storm begins because this blob of warm air is colliding with this cold air. And then this cold air is colliding with that blob of warm air. So this is warm and moist, cold and dry, cold and dry. So there's conflict because they're totally different in terms of temperature and humidity. So as they move along, and now we've got occlusion starting because the cold air mass, in fact, I'll just let it continue for a little bit. So after occlusion, the cold air is on the ground, the warm air has been lifted up. So in the troposphere, the surface is heated by the sun. The air next to the ground is heated by the ground. So the temperature profile of the troposphere should be the warmest air at the surface, and then as you go up, the air gets colder and colder and colder. Okay, but now everything's backwards. You've got cold air on the ground, you've got warm air lifted up. The cold, dry air was bouncing off of the warm, moist air because they had different temperature and humidity characteristics. Well, now the cold air along the ground is going to warm up. All the rain produced a lot of moisture and precip that's going to evaporate and humidify the cold, dry. So the cold, dry air is going to get humidified and warmed and become warm and moist. The warm, moist air got lifted up where it got cold, and as it got cold, you get condensation, so the warm, moist air is now cold and dry, and at some point there's no difference. The reason the cold air can lift the warm air is because of the difference in temperature. But once the warm air is lifted up, it gets cold. Once the cold air is on the ground now, it gets warm. So everything just kind of blobs together, and the storm just fizzles out because there's no more energy for conflict. So one more time, we've got the cold air catching up to the warm air. All that warm air is going to get lifted up. You're going to get more rain. But then the same process that started the storm is the same process that's going to end the storm, because there's no more moisture, there's no more energy. Midlatitude cyclones. Typically they take a couple days. The process of starting one is called cyclogenesis. Cyclo referring to cyclone with air flowing into an area of low pressure. And genesis means the birth or the start of. So it's how these storms start, usually along the polar front. With the open stage, the air starts to move around. The warm air is moving northwards. The cold air is moving southwards. The warm air is moving northwards with the westerlies, and the cold air is moving southward with the polar easterlies. After the open stage, you get rotation. You get a center of low pressure developing, and then both air masses start to rotate counterclockwise. You can then get occlusion when the cold air catches up with the warm air and actually passes the warm front because it's going faster. And then all the warm air gets lifted up and gets cold. All the cold air is on the ground, it gets warm, and then it just dissolves and goes away because there's nothing left to create conflict. The diagram out of the book is showing the same storm. Here it is in the open stage with rotation. And then over here, occlusion has already started. And the next thing that's going to happen, once you're in occlusion, here's the side view with the cold air and the warm air lifted up. Everything is going to mix together and the storm is just going to dissolve. We don't really get summer storms in California. We get winter storms when the Hawaiian high shifts south. Different diagrams showing the direction of wind, because one of the things that you'll notice is, and you should be able to read wind barbs, so we've got wind coming out of the southwest, wind coming out of the northwest. You can see the green arrows are indicating the direction of wind. So if you were right here in Wichita, in fact, even better, if you were right here, you'd be experiencing cold, clear, 40 degrees, dew point temperature of 28. And then after the warm front goes through, the wind is going to shift, and now the wind is coming out of the southwest, and it's warm and it's moist. And then after the cold front comes through, it's going to get really cold and really dry. Like the dew point's going from 69 down to 46. The temperature's going from 78 down to 47. The wind is coming out of the southwest, and now the wind is coming out of the northwest. So the wind direction is going to shift 90 degrees. Instead of being warm and moist and rainy, now it's going to be cold and dry and clear. Typically, that's what happens as a mid-latitude storm works its way through. So you have the same storm over 3 days with rotation, occlusion beginning, and then occlusion with the storm on its way to dissolving. Another diagram showing how a storm is going to work its way across the United States over the period of a couple days. You've got the warm air and the cold air, and then with the occlusion, everything gets backwards and it dissolves. Here we've got one storm over 3 days, or you've got multiple cyclones. Yeah, usually there's 3 to 7 storms in the polar front on any given day. Here's the open stage. Here the wind is out of the southeast and it's cloudy. Wind is out of the southwest. Remember, the wind comes from the end blowing towards the circle. And then here the wind is coming out of the northwest. So you can see here, 66 degrees with a dew point of 63. Dew point temperature is the temperature. If you cool the air, it's going to get to 100% relative humidity at 63 degrees. Over here, 27 degrees. Over here, 18 degrees. So those dew point temperatures are very low. The bottom temperature is the dew point. The top temperature is the air temperature. So here the wind is coming out of the south. It's 66 degrees. Here the wind is coming out of the west, and it's 37 degrees with a dew point of 21. And I was going to say, this is already in occlusion, so the next thing it's going to dissolve, and it's toast. Let's back that up. So there's day 1, day 2. Once you have occlusion, once it's in the occluded stage, it's on its way to dissolving because the warm air has been lifted up where it's cold. The cold air is on the ground where it's warm. Mid-latitude storms. Weather forecasting. What do we look at? They collect a lot of data. Lots and lots and lots of data. It's a good thing we have computers. They look at air pressure, whether it's rising. If it's rising, you're going to have clear weather. If it's falling, you're going to have stormy weather. The temperature, dew point temperature, wind speed and direction, type and movement of clouds, current weather, current sky conditions, visibility, precip. And then they feed it into computer models. They also use weather satellites, automated surface observing systems. AWIPS is their computer program that they use. Doppler is one of the ways that they measure how much rain or snow is falling, how strong the wind is, which way it's blowing. They can do all of that with Doppler radar. This is an automated surface observing system. Some parts of this are actually on the bridge going over Highway 80. I think it's probably fog. The visibility sensors, that's how they can find out if there's fog without people being there. Freezing sensor would be very important on a bridge because they're not connected to the ground, cool off faster, and so bridges tend to freeze faster than the roads on either side. So if you're going to skid off the road on ice, it's probably going to be on a bridge. So a lot of places where that's a problem, they'll have freezing sensors to let people know that the bridges are icing over. Weather computers. This is Doppler radar of the tornado that took out Moore, Oklahoma. You can see it's got this comma shape, the distinctive hook signature of a tornado. Here's an article about how they can use Doppler to track birds. The National Weather Service publishes weather maps. So at this point, you should be able to read this map and go, oh, that's a warm front. So the wind is probably coming out of the south-southeast. Here's an occluded front. Here's a cold front. So the wind is probably coming out of the northeast, east-northeast, coming from this direction, moving that way, making the front, maximum temperatures, minimum temperatures, all that. Elements of the daily weather map published by the National Weather Service. Also, the dotted line is showing the freezing isotherm, the parts of the country. And you'll notice they're inland, right? Not the coastal areas, not Florida, but parts over the Rockies. Yeah, parts over the Sierras. So high latitude is freezing, high altitude is freezing. Violent weather. So violent weather, we're talking about thunderstorms, derechos. We're talking about tornadoes and hurricanes. Violent weather is powered by the latent heat of condensation. So thunderstorms, which cause turbulence and lightning and thunder and hail. Derechos, tornadoes, tropical cyclones. Hurricanes and typhoons are just regional names for cyclones and hurricanes. We'll talk about tropical cyclones, but all of these types of violent weather are powered by the latent heat of condensation. As the air cools, the water vapor condenses. When the water vapor condenses, it releases heat back to the air, so the air gets warmed up a little bit, so it rises, so it expands and cools, and the whole process starts again. So there's a really interesting positive feedback loop required for thunderstorms and tornadoes and derechos and hurricanes. Days with thunderstorms, another way of thinking this would be, where are the places in the United States that have lots and lots of water vapor and high temperatures? And the winner is Florida. Go, Florida, man, go. Cumulonimbus clouds become thunderstorms. Lightning, thunder. You have rising air, creating an area of low pressure, which draws in more warm, moist air, which rises to the troposphere, sheared off by strong winds. You get rain. Rain makes downdrafts. You get lightning, flashes of light caused by electrical discharges. The lightning causes a sonic boom called thunder, and if you see the flash and you start counting, every second it's 1,000 feet. So the difference between the speed of light and the speed of sound means that if you see the flash and you start counting, so flash, 1,000, 2,000, 3,000, 4,000, 5,000, boom, you're 5,000 feet or about a mile away from where the lightning was. So every second that you count, it's about 1,000 feet. Within the cloud, the air and the water moving and swirling creates static electricity. The positively charged particles seem to gather in the top. The negatively charged gathers at the bottom. Earth at the ground is positively charged. And the first thing that happens is there's a stroke from the ground to the cloud. And then along that same path, there's a series of return strokes. Bam, 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 bam. And it all happens so fast that our brains can't process it. It all happens so fast that our brains can't process it. So we see it as one flash, but it's actually one flash up and then a bunch of flashes down. And that bolt of lightning, it's about the diameter of a garden hose, and it actually pushes the air molecules apart. And then when the bolt passes through, those air molecules crash back together, creating a sonic boom and thunder. I've included, yeah, it doesn't look like it. I've included some videos of lightning, some slow motion shots of lightning. This is a lake in Venezuela that's one of the most lightning prone regions in the world. It's in Venezuela, so it's close to the equator, so you've got warm tropical air masses and updrafts. Here is the spatial distribution. You can see, oh look, cold current, cold current, cold current, fewer thunderstorms. Warm current, more thunderstorms. Warm current, more thunderstorms. Right on the equator, more thunderstorms. So here is a diagram showing a thunderstorm, showing a cumulonimbus cloud rather, with the updrafts, and then the whole storm is going to move along from, in this case, left to right, pulling up warm, moist air that's then going to fall and make a downdraft and a gust front. And it's this downdraft and gust front that's going to make derechos. So as this whole system moves along, you can get intense, very strong winds coming off the front, winds over 60 to 100 miles an hour, winds that are hurricane strength coming off in a straight line, not curved like a tornado, but coming off in a straight line towards the front, making a derecho. But these updrafts and downdrafts are what make the hailstones get larger. The water goes up and it freezes, and then it falls down, it gets picked up, and it gets another layer of water that freezes, and it gets bigger until it's heavy enough to fall through the updraft, which, as I said before, can be 125 miles an hour. So again, same thing, you've got updrafts, you've got downdrafts. This is another shot of the world's largest hailstone, 1.75 pounds. It had a circumference of 17, 18 inches, enormous. Associated with thunderstorms are derechos. They're straight line winds over 58 miles an hour. They come off the front of these huge thunderstorms. They're very common across the East Coast. We don't really get them in California because of our topography, but on the East Coast, there's larger areas that are just flatter, which plays a role. So here was one derecho going across 2 o'clock in the afternoon, going across Michigan, 4 o'clock. You can see the wind speed, 41, 91, 84, 68, 70, 71, 70, 66, 70. Doesn't really seem like the wind speed dropped off a whole lot. From 2 o'clock to 4 o'clock to 5 to 6 to 7 to 8 to 9 to 10. So these are snapshots. It's not like this was at one time. At 2 o'clock, that's where it was. 3 o'clock, 4 o'clock, 5 o'clock, swept across the entire eastern seaboard from 2 o'clock till midnight with, you can see, 60 to 80 mile an hour winds. Also associated with the latent heat of condensation are tornadoes. So to make a tornado, you need to have cumulonimbus clouds. You need to have horizontally rotating bodies of air that get lifted vertically by updrafts. If that rotation touches the ground, it's a tornado. If it's over water, it's a waterspout. So, right, as you all know, there's friction. Wind against the surface, there's friction, so the wind speed towards the ground is slower than the wind speed aloft. So the higher wind speed aloft will actually create horizontal rotation of the atmosphere, like a rolling pin. A big chunk of the atmosphere is going to go rolling across the countryside. If it runs into the updraft of a cumulonimbus cloud, instead of rolling along horizontally, now it's rotating vertically. Bada boom, bada bing, you get a tornado. Here's the diagram out of the book. Stronger winds, weaker winds, making horizontally rotating air that then gets tipped on its end by running into the updraft of a thunderstorm, and then you have a tornado. Some of the highest wind speeds on the planet, I think over 321 miles an hour, was not measured, but calculated from a video of a tornado. the United States is uniquely suited to make tornadoes in the Midwest. We have warm, moist air coming off the Gulf of Mexico. We have cold, dry air coming off the Rockies. So the cold air burrows under the warm air. It gets lifted up in this region called Tornado Alley. We measure them on the enhanced Fujita scale. North America gets more than anyone else on Earth. Although there is some evidence that Tornado Alley, as a result of climate change, is shifting to what they're calling Dixie Alley. The blue bars are average tornadoes per month, 1950 to 2000. The red bars are the average tornadoes per month, 1991 to 2010, showing the increase in tornadoes partially because of global warming. If there's more energy in the atmosphere, you'd expect more stuff to happen, and also because people have more cell phone cameras. Back in the day, if there was a tornado, they had to send somebody from the Weather Service to come out and actually look at the ground. And if there were swirl marks, there was a tornado. If there aren't, it wasn't a tornado. Even if you saw one and the Weather Service couldn't establish that it happened, it didn't count. But if you've got a video, it happened. So there's been an uptick in tornadoes caused by global warming, and there's also more tornadoes being recorded because everybody has a camera on their phone. And here's what I was talking about before. There's a demonstrated shift in tornadic activity from Texas over into Louisiana and Mississippi, Arkansas, Tennessee. There's been an increase in energy released by tornadoes. There's an increase in the number of tornadoes. All of this is associated with global warming. If you like tornadoes, you should live in the places with red dots. Tornado probabilities. And I think this is an animation. Oh yeah, showing over the course of a year how they follow the sun north. Whoa. Yeah, let's try that again. Speed. So now we're in October, November. Yeah, I don't care about December. Oh, now we're getting into spring. As it warms up, more tornadoes, more tornadoes. As it keeps warming and the sun keeps going farther north. And now we're getting into shifting back south. Yeah, that's a fun animation. Oh, this is Greensburg, Kansas, after an EF4 tornado went through. It mostly erased most of the town. You can see there's a few places left, but complete and total destruction in Greensburg, Kansas. More Oklahoma looked very, very similar. Tropical cyclones. Okay, so now we're going to get into the last part of extreme weather we're going to talk about. Those are tropical cyclones. So we talked about midlatitude cyclones, which form along the front caused by the warm air masses and the cold air masses. But if you're in the tropics, it's all warm and moist. So the air is uniformly warm and moist. I put a link down here to the Weather Service's Jetstream information service that has brief informational pages on various weather topics, including here's what you need to know about tropical cyclones. So I would check that out. It's got important information that can help you understand and enjoy this part of the chapter on tropical cyclones. So to make a tropical cyclone, you need water temperatures over 26 Celsius, 82 Fahrenheit, about that, for them to start. So what this is really showing you is regions of the world that have water over 26 degrees during these months. So June through October, June through November, June through December, April through December, and then the opposite, November through May in the southern hemisphere because they're 6 months out of phase. You'll notice there's a big gap that you can't have a tropical cyclone within 4 degrees of the equator because there isn't the Coriolis deflection required to get them to organize into the big swirling counterclockwise storm that makes a tropical cyclone. So not enough Coriolis deflection in this region. Here's a map of all the cyclone tracks, 1856 to 2013. And again, you'll notice that there's that gap right on the equator. Total of 1. The The South Atlantic is very small compared to the Pacific. So the larger the ocean is, the warmer the water can get. As the water moves with the trade winds across the equator, it gets warmer and warmer and warmer. The Atlantic is small enough that they've only had one. That was 2005 Hurricane Katrina. You can also see the effect of the clockwise rotating ocean currents, that there's a warm current, warm current, warm current, cold current. So when the hurricanes turn up into the cold water, they die because there's no water evaporating. Remember, it's the latent heat of the water vapor condensing that powers these things. So you need to have a constant supply of warm, moist air. So you don't get cyclones over cold water. You also don't get them, they don't form over the land. And typically when they move inland, they get cut off from their sweet supply of water vapor. So they just fizzle out. There's a close-up view. You can see that they try, but they die. Sea surface temperatures, August 27, 2005. This was around the time of Hurricane Katrina, when temperatures in the Gulf of Mexico, the sea surface temperatures were hitting 90, 91 degrees. Remember, you need over 26, 79, 80, 82 degrees to form, but conditions are often much warmer than that in tropical oceans. Tropical cyclones begin with easterly waves, these slow-moving waves of low pressure that move from the east to the west, embedded in the trade winds close to the equator. If conditions are right, you'll get low pressure developing at the surface. The whole system starts rotating and getting more organized, and then that positive feedback loop will take over. The rising air acts as a chimney, which pulls in more warm, moist air. So here's an easterly wave. They move from east to west with low pressure, so there's rising air. So you get air rising and expanding and cooling. As it cools, you get water vapor condensing, which releases heat. So the air rises, so the whole thing keeps going. The eye wall has the most intense wind and rain. They have these really distinctive, the whole thing is rotating counterclockwise. You get these big bands of rain. You can see convection towers, which are the tops of cumulonimbus clouds. And in the eye, it's clear and there's no wind and it's sunny. Here is a cross section through Hurricane Gilbert. They flew one of these storm chasing airplanes through it. You can see how strong the eye wall is, and that there's no clouds in the eye. Air is actually sinking in the eye. And then you're back to the bands of rain on either side of the eye. Tropical cyclones move along at 10 to 25 miles an hour. They're measured with the Saffir-Simpson scale. Once they get to 75, 74, 75 miles an hour, they're a Category 1 hurricane. At 96 miles an hour, they'd be a Category 2. Above 157, they're a Category 5. And one of the most dangerous and damaging aspects of a tropical cyclone is storm surge. It's a bulge of water from low air pressure and high winds that forms under the tropical cyclone. The sea level actually rises under the hurricane because the low air pressure. There's less weight of the atmosphere on the ocean, so it bounces up a little bit, and then the storm pushes that ahead. Here we've got a hypothetical tropical cyclone. The whole thing is spinning counterclockwise and moving in this direction. So the front right corner is the worst, the most damaging, because the speed and direction of rotation, the rotation going counterclockwise, and the speed and direction of movement, if it's moving that way and it's going counterclockwise, the winds on this side get added. So if it's moving 50 miles an hour with 225 kilometer an hour winds, 175 miles, yeah, I'll get it right eventually. The hurricane is moving at 50 kilometers an hour. The wind speed on the left and right sides is 175 kilometers. So on this side, the wind is moving that way, the storm is moving that way, so the net wind speed is 225. On this side, what would that be? The lower left quadrant? the storm is moving that way, but the wind is moving that way, so they cancel each other's speeds. So it's moving 50 kilometers an hour, the wind speed's 175, so on this side, the wind speed is 125 kilometers an hour. 225, 125. Actually, 50 kilometers, that would be really, really rapid. I think some of the more recent hurricanes, one of the trends with global warming is that they're actually moving along more slowly. So not the wind speed necessarily, but just the speed that they move over Earth's surface, which means that, well, as they're moving along, there's enormous amounts of rain underneath. So you're getting more rain because the storms are moving more slowly. And here we've got Hurricane Harvey down here. In fact, Hurricane Harvey is a great example of this. You can see the counterclockwise rotation. You can see daily thunderstorms popping off. Convective activity. Here we've got Harvey picking up strength. Everything's rotating counterclockwise. It's another day. So then in the afternoon, we've got little popcorn convective clouds. You can see Cuba going off with convective activity in the afternoon. Sun shines in the ground gets warm, the air rises, you get clouds. And Harvey moved very, very slowly. One of the most damaging aspects of Harvey was the rainfall, and the damaging aspect of the rainfall was that the storm moved so slowly that it just kept raining and raining and raining in the same spot. Storm surge. So underneath the hurricane, you get high wind, and the high wind makes high waves. So you've got high wave heights, but then the height of the ocean also rises. So now you have higher sea surface levels along with higher wave height, and all of that combines to make storm surge. So in this example, we've got a 17-foot tide, a 17-foot storm tide with a 2-foot normal high tide. That should be 19. I don't know what they're doing with their math. It doesn't matter. Here are some projections of storm surge with one of the hurricanes. Like right here, 9-foot storm surge, 6 feet, 6 feet, 3. Ah, perfect. Yeah, if the storm goes away and there's sand from the beach in your house, it's a good indication that there was really extreme storm surge. So the ocean would have come in all this way. I'm not sure which way we're looking at. Let's look at another one. This is from Hurricane Ike. This is Hurricane Ike in 2008. This is the Bolivar Peninsula. And I think Ike had a 15-foot storm surge. So the houses that they're pointing out, I think these were 2 houses that were designed to be hurricane proof. And this is on a barrier island off of Texas. This was before Ike moved on shore. And that's after. And in some of the more detailed pictures, you could actually see where the sand had built up on the leeward side of houses, that the waves were coming in from the bottom, moving towards the top. And where the houses used to be, on the inland side, there were sand dunes. There were sand dunes in the shadows of where the houses used to be from Ike. That you can see the highest point on the island is like 6 feet above sea level. So if you had a 15-foot storm surge, that means that most of this would have been under 11 feet of water. So the highest, I keep saying, the highest part of this island is like 6 feet above sea level. That's about what we're looking at in terms of sea level rise in the next 100 years. So the sea level is coming up. The storms are getting bigger. They have septic tanks. When you flush the toilet, it goes into a tank just below the surface of the land. So when the whole island gets flooded, everything in the septic tanks comes out and gets mixed in and then spread out. So I look at this and think, I can't imagine rebuilding. Like, I think these are mainly vacation homes on the Gulf, but still, the idea of like rebuilding, why? We know that the storms are getting bigger. From 1970 to the present, the energy released by storms has doubled. So we know the storms are getting bigger, and we know that sea level is rising, and that the highest point of this island is 6 feet above sea level, and we know that the ocean is expected to rise in sea level by 6 feet in the next 100 years or so. So why would you build there? Don't know. Hurricane Camille. Hurricane Camille. Camille is one of those names that's been retired. There will never be another Ike. There will never be another Katrina. There will never be another Hurricane Camille. Just like LeBron, they retire the jersey. They retire the name after an especially deadly hurricane. These are the Richelieu Arms apartments in Mississippi. This is sand because we're right across the street from the beach. These people were ordered to evacuate. They evacuated, which was a really good thing, because that's the way the apartment building looked after. In fact, this hurricane, Hurricane Camille, I'm going to back up and say, when Hurricane Camille came on shore, there were 100 tornadoes going off simultaneously in the front right quadrant of Hurricane Camille. So I said it's the most dangerous, most damaging spot to be in. As an example of that, when Hurricane Camille blew on shore in 1969, there were 100 tornadoes going off in the middle of the hurricane. In fact, storm surge from Superstorm Sandy did a lot of damage to New York City. New York City has allocated a couple $2 billion to try to prevent future storm damage by flooding. So they're taking anti-flooding measures in New York City to the cost of about $2 billion, I think, to prevent even more expensive damage later. Yeah, that's after Hurricane Sandy. This was the boardwalk in New Jersey. If your roller coaster's in the ocean, you might have had a hurricane. And then finally, this video is in the lecture slides. I'm not going to show it, but it's an animation. It's one of my favorite animations of the 2005 storm system, which is a good analog for our current storm system, because our current storm system, our current storm season, I think that was Katrina. So you can see these waves. I'm going to pause it because otherwise I'm going to try to talk about it and say that in 2005, we ran out of names and had to start using Greek letters: alpha, beta, delta, gamma, epsilon, zeta. And already in 2020, we have run out of the names. The official list of names has been used up, and we're already up to beta, and it's only September. So it's a great video. A couple times, the things that they talk about in the video, the animations are great. So they start off with these storms, just looking at the clouds, and then they're going to bring in, they bring in sea surface temperatures and show the maximum water as of October. So warmer and cooler sea surface. You can see the ocean currents bringing that warm water up. Anyway, you can see the westerlies coming across. You'll see daily convection patterns. You'll see these. There's the ITCZ. You'll see the trade winds moving these storms across. And sometimes you'll pick out one at I like to look at the bottom of the screen and see if I can't track them as they go across. Like right there, looks like there's something. If you keep moving, there it is. And I don't know what that did. That did nothing. Another one. Maybe. Oh, Cindy. Oh, Dennis. Anyway, I would watch that a couple times. Pay attention to the narration. It's a great video. They talk about the role of sea surface temperatures. They talk about the ocean being warm. They talk about other factors that prevent hurricanes from getting really powerful. Well worth your time. And that's it for violent weather. And that's the end of atmospheric water and weather, part 2 of chapter 4. Easily, I think, the toughest chapter out of the entire semester. So I hope you enjoy chapter 4. If you have questions, please come to Zoom. And I hope you enjoy chapter 4.